Welcome to this problem walkthrough. In this session, we'll solve LeetCode problem number 1487, titled Making File Names Unique. This problem challenges us to implement an efficient and systematic approach to handle duplicate file names. Let's dive into the details and explore various approaches to solve it. In this problem, you are given an array of strings called names, where each string represents a file name. The challenge is to ensure that every file name in the array is unique. If a file name already exists, you need to modify it by appending the smallest suffix k in the form of k, so that the resulting name becomes unique. Once all the names have been processed, you should return an array called result, where each element corresponds to the unique name assigned to the respective file in the original array. For the input, you'll receive a list of strings, and the output will also be a list of strings representing the unique file names. Let's look at an example to better understand how this works. Suppose the input names array is GTA, GTA 1, GTA, Avalon. The output for this example would be GTA, GTA 1, GTA 2, Avalon. Here's why: the first file name, GTA, is unique, so it remains unchanged. The second file name, GTA 1, is also unique, so no modification is needed. However, the third file name, GTA, is a repetition of the first one. To make it unique, we append the smallest suffix, k equals 2, resulting in GTA 2. Finally, Avalon is unique, so it remains as is. Another example demonstrates how the solution handles more complex cases. Consider the input names equals doc, image, doc1, doc. For this input, the output would be doc1, image, doc1, 1, doc2. Here's how we arrive at this result. The first occurrence of doc is unique, so it stays as doc. The second occurrence of doc is a duplicate, so we append k equals 1, making it doc1. Image is unique and remains unchanged. The next file name, doc1, is a repetition of the modified name from earlier. To make it unique, we append k equals 1 again, resulting in doc1, 1. Finally, the last occurrence of doc is a duplicate, so we append k equals 2, giving us doc2. Now, consider an example with all identical file names, names equals The output for this case would be A1, A2, A3. The first occurrence of a is unique and remains unchanged. For each subsequent occurrence, a suffix is appended to create a new unique name. Specifically, A1, A2, and A3 are generated by appending the smallest possible suffixes. Moving to the constraints, the input array can have up to 50,000 file names, where each name can be up to 20 characters long. The names may include lowercase letters, digits, and round brackets, and all names are guaranteed to be valid. Special cases to consider include scenarios where all names are unique, where all names are identical, and where names already contain suffixes like 1. Efficient handling of large inputs is critical to solving this problem within the constraints. To address the problem of making file names unique, we first considered a brute force approach. The intuition behind this method is straightforward. As we iterate through the list of file names, we check if a name already exists in the output list. If we encounter a conflict, we append a suffix, such as k, or k starts at 1 in increments until the name becomes unique. While this method is simple and directly solves the problem, it has significant performance drawbacks. Resolving conflicts often requires scanning the output list multiple times, leading to a worst-case time complexity of n squared, where n is the number of file names. Additionally, while the space complexity remains n, to store the output, the inefficiency in runtime makes this approach unsuitable for larger inputs, especially when n grows to 10,000 or more. For these reasons, the brute force approach was ultimately not chosen. Instead, we turned to an optimized approach using a hash map. The key idea here is to track the next available suffix for each base file name in constant time, eliminating the need for redundant scans. By leveraging a hash map, we can ensure that each conflict is resolved efficiently. Specifically, we start with an empty hash map called name_count and iterate over the list of names. If a name is not yet in the hash map, we add it directly to the result and set its count to 1. However, if a conflict arises, we use the smallest available suffix, tracked in the hash map, to create a unique name, and then update the map accordingly. This approach reduces the time complexity to O(n), as each name is processed once, and the space complexity remains O(n) for both the hash map and the output list. The hash map approach was chosen because it avoids the inefficiencies of the brute force method and performs well even for large inputs. The optimized hash map approach emerged as the clear choice for solving this problem. Its linear time complexity and straightforward implementation make it far superior to the brute force method, which struggles with performance bottlenecks as the size of the input grows. The key insight that made this solution possible was recognizing that by tracking the next available suffix for each name in a hash map, we could avoid redundant checks and resolve conflicts in constant time. This method is not only efficient but also robust, handling edge cases like duplicate names with existing suffixes seamlessly. Of course, there are trade-offs to consider. The hash map approach does use slightly more memory compared to the brute force method, as it requires additional space to track the counts for each name. However, this memory overhead is a small price to pay for the dramatic improvement in runtime, especially when dealing with larger datasets. Ultimately, the hash map approach strikes the best balance between efficiency, readability, and scalability, making it the most practical choice for this problem. The problem we're tackling involves making file names unique. You are given a list of file names, and the goal is to ensure that each name in the output list is unique. If a file name already exists, you need to modify it by appending a suffix in the format k, where k is the smallest integer that results in a unique name. The final output must preserve the order in which the file names are processed. To solve this, we can use a systematic approach that starts with initializing some key variables. First, we set up an empty dictionary called name_count to keep track of how many times each base file name appears. We also initialize an empty list called output, which will hold the unique file names in the correct order. Then, we iterate through each file name in the input list. If a file name is not already in name_count, it means the name is unique, so we can directly add it to that output list while also updating name_count to indicate that this name has now been seen once. When we encounter a file name that already exists in name_count, it means we need to make that name unique. To do this, we retrieve the current count of the file name from name_count. This count helps us determine where to start appending suffixes. Using a loop, we generate modified names by appending k, starting with the current count as k. We then check if this modified name exists in name_count. If it doesn't exist, we've found a unique name and can exit the loop. Otherwise, we increment k and keep trying until we find an available name. Once a unique name is generated, we add it to the output list and update name_count for both the original base name and the new unique name. The count for the base name is also updated to reflect the next suffix that should be tried. Finally, after processing all file names, the output list, which contains all the unique file names, is returned as the result. What makes this algorithm efficient is its use of a greedy approach to resolve duplicates. By incrementing k step by step until a unique name is found, we ensure that the first available suffix is used, minimizing unnecessary iterations. Additionally, the use of a dictionary for name_count allows us to perform constant time lookups and updates, which is crucial for maintaining efficiency as the input size grows. The algorithm is also designed to handle various edge cases. For example, it works correctly when the input list is empty, when all file names are initially unique, or when there's a mix of unique and duplicate names. It even handles extreme cases where all file names are duplicates of a single base name. By using a dictionary and a list, we ensure that the algorithm is both time efficient and respects the order of input processing. In terms of complexity, the time complexity of the algorithm is O(n*(m). Here, n represents the number of file names in the input list, and m is the average number of suffix checks required to resolve duplicates. This complexity arises because for each file name, we may need to perform multiple suffix checks until a unique name is found. The space complexity is O(n), as we use the name_count dictionary to store the counts of both base and modified file names, and the output list to store the final result. Now, let's walk through an example to see how the algorithm works step by step. Consider the input list, file, image, file, 1, file. We'll process each file name one by one, keeping track of name_count and output along the way. Starting with file, we find that it's not in name_count, so we add it to output and set its count in name_count to 1. Next, we process another file. This time, it's already in name_count with a count of 1, so we generate file 1 as the unique name, add it to output, and update name_count. Then, we handle image, which is unique, so it's directly added to output, and its count is set to 1. When we encounter file 1, it's already in name_count, so we generate file 1 as the unique name, add it to output, and update name_count. Finally, we process another file, which now has a count of 2 in name_count. We generate file 2 as the unique name, add it to output, and update name_count. The final result is file 1 image file 1 file 2, which ensures all file names are unique while maintaining the input order. This Python implementation solves the LeetCode problem number 1487, making file names unique, by ensuring that each file name in the input list is unique in the output list. The solution uses a dictionary to track the occurrences of file names and efficiently manage the creation of unique names. The getFolderNames function begins by initializing an empty dictionary name_count to store the number of times a base file name has been encountered. It also initializes an empty list result to store the final list of unique file names. The function then iterates over each file name in the input list names. If the current file name does not exist in the name_count dictionary, it is directly added to the result list, and its count is initialized to 0 in the dictionary. If the file name already exists in the dictionary, the function computes the smallest integer k such that appending k to the file name results in a unique name. This is achieved using a while loop that increments k until the new name is not found in name_count. Once a unique name is found, it is added to the result list, and both the new name and the updated count for the base name are registered in the name_count dictionary. This approach ensures that each file name is processed in O(1) average time due to the efficient dictionary operations. The overall time complexity of the solution is O(n), where n is the number of file names in the input list. The space complexity is also O(n), to store the dictionary and result list. The code handles edge cases, such as multiple duplicate names and names that require high suffix numbers, by dynamically checking and generating unique names as needed. This ensures correctness and efficiency across all inputs. Here, we begin by importing the necessary utilities and defining our solution class. Inside it, we have the method getFolderNames, which takes an array of strings called names. This method is tasked with ensuring all file names in the input array are made unique. To accomplish this, we use a hash map called nameCount to keep track of how many times each base name has occurred. We also initialize a result array of the same length as the input, which will store the final unique file names. Now, we iterate over the input array using a for loop. For each file name in the array, we first check if it is already unique by seeing if it exists in the nameCount map. If it doesn't, we can directly assign it to the result array at the current index and add it to the map with an initial count of 0, indicating no suffix has been added yet. However, if the name already exists in the map, we need to generate a new name by appending a numeric suffix enclosed in parentheses. To find the correct suffix, we start with the next available number and keep incrementing it until we arrive at a name that is not already in the map. Once we determine this unique variant, we add it to the result array and also update the map to reflect its usage. Finally, after processing all the names in the input array, we return the result array containing the unique file names. This ensures that every name in the output is distinct, even if the input had duplicates. The use of a hash map allows us to efficiently check for existing names and manage the counts for each base name and its variants. With this, we've successfully implemented the solution to make file names unique in Java. In this example, we start with the input array containing 4 strings, file, 1, and file. First, we initialize 2 structures, an empty dictionary called name_count to track the usage of each name and an empty list called result to store the final output. Now, we process the first string, file. Since file is not in name_count, we add it directly to result, making result equal to file. We then initialize name_count, file, to 0, indicating that the base name file has been used. Next, we encounter file again. This time, it is already in name_count, so we calculate k as 1, which is name_count, file, plus 1. The name file, 1, does not exist in name_count, so we add it to result, updating it to file, 1. We also register file 1 in name underscore count and update name underscore count file to 1 to reflect the new count of the base name. Now, we move on to file 1, which is already present in name underscore count. Calculating k as name underscore count file 1 plus 1, which equals 1, we generate the new name file 1, 1. Since this name is not in name underscore count, we add it to result, resulting in file 1, 1. We also register file 1, 1 in name underscore count and update name underscore count file 1 to 1. Finally, we process file once more. Using the current name underscore count file value of 1, we calculate k as 2. The name file 2 does not yet exist in name underscore count, so we add it to result, which becomes file 1, 1, file 2. We register file 2 in name underscore count and update name underscore count file to 2. The final output for this example is file 1, 1, file 2. In the second example, we have the input array doc 1, doc 1. We start by initializing name underscore count as an empty dictionary and result as an empty list. The first string is doc, which is not in name underscore count. We add it to result, making result equal to doc and initialize name underscore count doc to 0. The next string is also doc, which is already in name underscore count. We calculate k as 1, which is name underscore count doc plus 1. The name doc 1 does not yet exist in name underscore count, so we add it to result, updating it to doc 1. We then register doc 1 in name underscore count and update name underscore count doc to 1 to reflect the new count of the base name. Next, we process doc again. Since doc is in name underscore count, we calculate k as name underscore count doc plus 1, which equals 2. The name doc 2 is not in name underscore count, so we add it to result, resulting in doc 1, doc 2. We register doc 2 in name underscore count and update name underscore count doc to 2. Now, we encounter doc 1. Since it is already in name underscore count, we calculate k as name underscore count doc 1 plus 1, which equals 1. The name doc 1 is not in name underscore count, so we add it to result, updating it to doc 1, doc 2, doc 1. We then register doc 1 in name underscore count and update name underscore count doc 1 to 1. Finally, we process doc 1 once more. Since doc 1 is in name underscore count, we calculate k as name underscore count doc 1 plus 1, which equals 2. The name doc 2 is not in name underscore count, so we add it to result, resulting in doc 1, doc 2, doc 1, doc 2. We register doc 2 in name underscore count and update name underscore count doc 1 to 2. The final output for this example is doc 1, doc 2, doc 1, doc 2. In the third example, the input array is test 1, test 1, test 2. We begin by initializing name underscore count as an empty dictionary and result as an empty list. The first string, test, is not in name underscore count, so we add it to result, making result equal to test and initialize name underscore count test to 0. The next string is also test, which is already in name underscore count. We calculate k as 1, which is name underscore count test plus 1. The name test 1 does not exist in name underscore count, so we add it to result, updating it to test 1. We then register test 1 in name underscore count and update name underscore count test to 1. Next, we process test 1, which is already present in name underscore count. Calculating k as name underscore count test 1 plus 1, which equals 1, we generate the new name test 1. Since this name is not in name underscore count, we add it to result, resulting in test 1. We register test 1 in name underscore count and update name underscore count test 1 to 1. Then, we process test 1 again. Using the updated value of name underscore count test 1, which is now 1, we calculate k as 2. The name test 2 does not exist in name underscore count, so we add it to result, updating it to test, test, 1, test, 1, 1, test, 1, 2. We register test, 1, 2, in name_count and update name_count, test, 1, to 2. Finally, we process test, 2. Since test, 2, is not in name_count, we add it directly to result, resulting in test, test, 1, test, 1, 1, test, 1, 2, test, 2. We register test, 2, in name_count and initialize its count to 0. The final output for this example is test, test, 1, test, 1, 1, test, 1, 2, test, 2. The time complexity of this solution is determined by analyzing the loops and operations involved. First, we have the outer loop, which iterates over the input list names. If there are n file names in the list, this loop runs exactly n times, once for each name. Inside this outer loop, there is a while loop that handles the process of finding a unique name for duplicates. This inner loop checks if a candidate name, such as name, k, exists in the dictionary name_count. Thanks to the hash table implementation of dictionaries, these lookups happen in constant time, or O1, on average. The number of iterations of the inner loop varies depending on how many duplicates exist for a given name. However, a key observation here is that every unique name and variant is added to the dictionary, and there can be at most n unique names. This means that while individual iterations of the inner loop depend on conflicts, the total number of checks across all names is bounded by n. As a result, the total cost of all inner loops combined is O(n). To further refine the time complexity, we examine the cost of string operations within the solution. When generating a new name, such as name, k, the process involves string concatenation and formatting. The cost of this operation depends on the length of the base name, represented as L, and the number of digits in k, which is proportional to log 10, k. In the worst case, this cost is dominated by L, the length of the longest base name. Combining this with the earlier analysis, the total time complexity of the solution becomes O(n*L), where L is the average length of the file names. For space complexity, we consider the main contributors, the dictionary name_count and the result list result. The dictionary stores all unique names, including base names and their variants. In the worst case, this requires O(n*L) space, as there are n entries, and each string entry has an average length of L. Similarly, the result list also stores n names, requiring another O(n*L) space. Together, these lead to an overall space complexity of O(n*L). In addition to the dictionary and result list, the solution uses a few auxiliary variables, such as k for the integer suffix and new_name for temporary storage of new file names. However, the space required for these variables is negligible compared to the space used by the dictionary and result list, so they do not impact the overall complexity. This brings us to the comparison with a brute force approach. In a naive solution, we would repeatedly check if a name exists in the result list and append a new variant if necessary. This requires O(n) time for each lookup in the list, and generating unique variants for duplicates could involve multiple such checks. This inefficiency results in an overall time complexity of O(n²), which is significantly worse than the given optimized solution. The optimized approach, on the other hand, leverages the constant time lookups provided by the dictionary name_count to reduce the time complexity to O(n*L). Additionally, the space complexity of O(n*L) is the best achievable for this problem given the need to store all unique names. Now, let's analyze the best, average, and worst cases for this solution. In the best case, all names in the input list names are already unique. Here, the solution only performs a single dictionary lookup for each name, resulting in a time complexity of O(n), as there are no inner loop iterations. In the average case, where the input contains a mix of unique and duplicate names, the inner loop runs for a subset of the names to generate unique variants. However, the total cost remains O(n*L), as we've seen that the number of inner loop iterations is bounded by n, and string operations add a factor of L. In the worst case, where all names in the input are identical, the solution must generate and check in unique variants. Even here, the dictionary allows each lookup and update to occur in constant time, keeping the overall time complexity at O(n*L). To summarize, the outer loop runs n times, the total inner loop iterations are bounded by n, and string operations contribute a factor of L. This reasoning confirms that the combined time complexity is O and *L, while the space complexity remains O and *L, due to the storage requirements of the dictionary and result list. When solving this problem, there are several common mistakes to watch out for. First, misunderstanding the problem statement can lead to incorrect solutions. For example, instead of appending a unique suffix in the required format, such as k, some might modify the name arbitrarily. This violates the problem's constraints and results in invalid outputs. It's important to strictly follow the prescribed format. Next, inefficient name lookups are another frequent issue. If you use a nested loop to repeatedly check for duplicate names, it results in an O(n)² time complexity, which is inefficient for larger inputs. A better approach is to use a hash map for constant time lookups and to track suffixes for each name. Another common mistake involves off-by-1 errors in the suffix. This happens when the suffix starts at 0 instead of 1 or when you fail to increment the suffix properly for persistent conflicts. To fix this, always initialize the suffix to 1 and increment it until a unique name is found. Finally, edge cases, such as handling an empty input list or names that already have suffixes like file, 1, are often overlooked. To avoid this, make sure to test your solution thoroughly with diverse edge cases to ensure it handles all scenarios correctly. Another mistake to avoid is modifying the input list directly while iterating over it. This can lead to unexpected behavior, as the list is being altered during the iteration. Instead, you should create a separate output list to maintain control over the changes. Moving on to interview insights, the hash map is the key data structure for solving this problem efficiently. It allows you to store the count or last used suffix for each name, ensuring constant time lookups and updates, which leads to an overall time complexity of O(n). It's also crucial to understand the constraints of the problem. For smaller inputs, such as n less than or equal to 10 cubed, a brute force approach may be sufficient. However, for larger inputs, optimizing for efficiency is essential. When discussing your solution during an interview, be prepared to explain the trade-offs between brute force and optimized solutions, emphasizing differences in time complexity. Additionally, proactively discussing edge cases demonstrates thoroughness and an attention to detail, which are key traits interviewers look for. This problem shares similarities with several other LeetCode problems that also rely on hash maps. For instance, in problem 3, longest substring without repeating characters, a hash map is used to track characters that have already been seen. In problem 49, group anagrams, hash maps are used to efficiently group strings based on their properties. Similarly, problem 128, longest consecutive sequence, focuses on the efficient use of hash sets to solve sequence-related challenges. Lastly, problem 219 contains duplicate 2, involves leveraging hash maps for efficient lookups and tracking indices. Exploring these related problems can help you strengthen your understanding of hash map-based solutions and improve your ability to tackle similar challenges. There are also alternative approaches to solving this problem, each with its own trade-offs. The brute force approach involves iterating through the list and repeatedly scanning the output list to resolve conflicts. While this method is straightforward to implement, it becomes inefficient for larger inputs because of its O(n)² time complexity. A more optimal solution is to use a hash map to track the last used suffix for each name. When a conflict arises, you increment the suffix until a unique name is found. This approach is slightly more complex to implement but achieves a much better time complexity of O(n). Another strategy is pre-processing the input for efficiency. If constraints allow, you could sort the input list alphabetically and then resolve conflicts in a single pass. While sorting introduces an O(n) log n complexity, it can simplify the logic for certain cases and make the solution more intuitive. Each of these approaches has its use cases, so understanding their trade-offs is essential to choosing the right one for the given constraints. Great job! We've solved the problem using an optimal approach that ensures efficiency and scalability. Remember, hash maps are a go-to data structure for problems involving uniqueness. Thanks for watching, and don't forget to like, subscribe, and keep practicing more problems. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!